Well, the quarter is coming to a close, and so is this series of lectures. Today, what we're going to do is continue our exposition of H2 plus and move on to H2. We're going to optimize our molecular orbital treatment of H2 plus, and then we're going to kind of throw in the towel because H2 would be at least as much work, if not more work, than helium if we did it from scratch. And so at that point, we're going to adopt a more qualitative view of molecular orbital theory, the kind of view that people in the business often use when they talk about bonding in much, much more complicated atoms and molecules that have many, many electrons and nuclei all over the place. We'll also touch on a very important idea called configuration interaction, and we'll see how that can influence the energies that we calculate and improve the results that we get. Well, where were we? At the end of the last lecture, what we tried to do is we tried to include a Slater 2s orbital to improve the energy for H2 plus. And what we found, without going through the whole calculation, but what the calculation concludes is that when we allow any amount of the 2s and 1s, basically it decides on its own that the 2s is not very important. It doesn't include very much of it, and the energy doesn't improve very much. And what that means, in fact, is that 2s was a very bad choice. I think you can kind of see why 2s might be a bad choice to include. It's a bigger sphere, and H2 plus is more like a sausage. And so if we want to get something to be more like the electron density that we expect in that molecule, we don't want to include another round thing. And basically the calculation concludes the same thing. Whenever you include orbitals and then you get very tiny coefficients, what that means is that you made a poor choice. If you were making them by intuition, you made a poor choice. And it's possible to make a bunch of poor choices, even using a computer, and spend a lot of computer time and then come to the conclusion that none of those orbitals contributes, none of those atomic orbitals or Slater orbitals contribute significantly to the final result. And so the question is, knowing that, how can we make a better choice? And in fact, this is quite important because even if you're using the computer to help you with a program like Spartan or Gaussian, you have to make an intelligent choice about the basis set or the orbitals you're going to include in the calculation. And if you include a lot of them that are irrelevant, that's like going down every dead-end street and staying to the right-hand side and going through a whole neighborhood rather than taking the boulevard straight through the calculation to get to the answer. Well, here's the idea. Supposing I'm a hydrogen atom and I have my spherical 1s orbital here, and I bring up a proton. The electron is going to be attracted to the proton, and so I expect that this orbital is going to stretch in that direction. In other words, it's going to be polarized by the presence of the other positive charge. And that stretching in one direction on the internuclear axis can't be represented very well by a sphere because a sphere moves out in every direction equally. And therefore, I don't want to use a spherical orbital. I want to use an orbital that's shaped more like this with some directionality. And because of that, what I want to use is in fact a 2pz orbital. That's what I have to use. There's no 1pz, of course. So I have to use a 2pz orbital, and that would have a plus and minus lobe, and I could direct it so that the electron density built up in the direction of the other nucleus. Of course, if I include 2pz, which has cosine theta in its functional form, then my integrals get a lot harder to do because now I have this extra theta and so forth. But if I include this 2pz in the original basis set, I can improve the results a lot. The integrals get harder. They aren't impossible. We could certainly do them all together, and if we had world enough and time, we could do that sort of thing. But I'm afraid that we won't be able to go through that in great detail and take 2 lectures just to simply do all those integrals one after another. Although it is fairly relaxing to occasionally decide to do a problem from scratch and go through it and understand every single thing about it. That's how you become an expert, of course. So here's what we're going to do. We're going to try a trial function here on slide 597 of the form some coefficient times 1SA plus 1SB plus some other coefficient C2 times 2PZA plus 2PZB. We have to keep things equal between the A and B because of the symmetry of the problem, but including these 2p orbitals lets us include polarization in the wave function. We know from experience how important this parameter zeta, the funny Greek squiggle, is in the exponent, and so we're going to just straight away use Slater orbitals. We aren't going to just stick to the hydrogen-like wave functions, because we've seen that every time we allow zeta to vary so that the things can stretch out a little bit, that we get much, much better results. So if we're trying to get better results, we might as well put zeta in. And then here are the forms, for the functional forms, for the 1s and the 2p z that we're going to include. There's zeta 1 for the 1s, and there's zeta 2 for the 2p. And of course, there's the r cosine theta that we get from a 2p orbital. When we first start out, though, it's simpler to let zeta 1 equal zeta 2. That's more restrictive, and then just optimize the coefficients C1 and C2, and then go back and optimize zeta. When you're optimizing the linear coefficients, the parts of the fixed things you're using, that's a pretty simple calculation to do. That amounts to linear algebra. When you start optimizing things in the exponent, it's much, much trickier, and usually it involves a lot more work. Oh, here's what we get then after quite a very long calculation. The minimum energy is minus 0.59907 in terms of Hartree, and the optimum internuclear distance, R sub E, is 2.00 times A naught, the Bohr radius. And this is with C1 equals to 1, and C2 is equal to 0.161. So about 16.1% of the PZ included when the two zetas are the same is the optimum. And that's quite a bit, and what that means is that we made a good choice, and we can see we made a good choice because the energy improved and the radius was much closer to the true experimental radius. And of course, the joint value of zeta is not 1, it turns out to be 1.247, so stretched out a little bit like it was before. There's an overall normalization in this to make sure that your whole molecular orbital is normalized, but the relative amounts are 1 and 100%, and so to speak, and 16%. And as I said, we get quite a bit of improvement by doing this. Now, if we let both of them vary, then our integrals are tougher, and we have these two parameters, and we end up with a very long formula at the end. And then, after all that, we have to optimize this long formula and find the minimum values of zeta 1 and zeta 2. And that's an even longer calculation, but we can do it, and it's not too bad. It can be done by hand even. It's not a big deal. It just takes time and patience. And if you do that, then you find that the minimum energy is now minus 0.60036. The radius is the same. C1 is 1. C2 is now 0.138, so 13.8%, changed a little bit. Zeta 1 is 1.2458, which is close to the value that we had before, and Zeta 2 is, for the p orbital, is 1.4224. The exact energy is minus 0.6020 ... And so we are very close with minus 0.600. Of course, with one electron only, the orbital approximation is not really an approximation at all because there's only one electron. So of course we would expect to be able to do very well once we get the form of the orbital down. We could include more terms. You can say, well, which ones would we include? Would we include a 2s pointing the other direction? The answer is no. That would do absolutely no good at all. Should we include a 3D that looks like a clover leaf with 4 lobes? The answer there is no. That's not going to help us at all. If we put a function like that in, its coefficient comes out to be essentially 0. We could put a 3dz squared, which is the unique one that looks a little bit like a p orbital with that ring around the center. And if we include 2 of those as well, and by that time we really do need a computer to do the calculation. Doing it by hand is just too much work. Then we can get very, very, very close to the exact answer for H2+. And that's really reassuring because in these simple systems, we better be able to get it right, and we better be able to get it right to a lot of digits. Otherwise, there might be something wrong with our whole underlying view in terms of wave functions and quantum mechanics. No one believes that there is anything wrong with quantum mechanics. It seems to predict everything very well, even though it makes surprising predictions about things like the double slit experiment. The H2 molecule, now, if I add another electron, that's the simplest neutral molecule that we can have. And it's just like helium now. With the 2 electrons, we have the electron-electron repulsion. We're back to that 1 over R12 there to integrate, only now we have to integrate it over a much uglier set of coordinates with the nuclei stretched out rather than being at one point. And so it's harder, and I'm not going to go through that because it's too hard, and I think you've got the idea now about how you undertake these calculations, even in a lot of detail. What we're going to do then is we're going to pretend that we can use orbitals that look rather like the ones that we had for H2+, and that we can just slot another electron in. Recall, that's what you do with atoms. You start with the hydrogen atom where you know the exact answers, and then you just start slotting electrons in, and of course what happens is the orbital energies get jumbled around and move around, but you still, in the orbital approximation, you think of a 3D orbital rather like something that you would find in hydrogen. Of course, they may be pulled in if the atom's bigger and the nuclear charge is bigger, but qualitatively we still think in terms of these kinds of shapes, and we still think in terms of shells, like the radial distribution function that we found in a much earlier lecture. We know we can put two electrons into the same spatial orbital, and the same bonding orbital that we found was the low energy solution, and the overall molecular orbital then is a Slater determinant, just like it was for atoms, because we have to have the spins be antisymmetric so that the total wave function is antisymmetric. And what we can write then is we can write that the bonding orbital is a linear combination of two exponentials. Let's say if we just use the 1sa and 1sb orbitals, we normalize it according to the overlap S in the denominator here, and we get this formula then for the bonding orbital. And then the Slater determinant consists of this bonding orbital and then the assortment of spin states. So we start with the bonding orbital and spin, the electron 1 is up, spin alpha, and then the bonding orbital electron 1 is spin down, beta, and then the second row we're referring to electron 2. We have again the bonding orbital for the spatial orbital, electron 2 is spin up, and the other final entry in the 2 by 2 Slater determinant is the bonding orbital times the spin function for the electron 2 being down. And I've expanded this out on slide 601, and then this is what we have now. We have the bonding orbital for electron 1 for the spatial part times, because remember that's how we do it, we always take a product, times the bonding orbital for electron 2, and then we have the spin part, which is the antisymmetric singlet part that comes from taking the determinant. And in this case, the spatial part is symmetric, obviously, and the spin part is obviously antisymmetric, which you can verify by swapping 1 and 2 and seeing that the wave function changes sign. As far as we're concerned, we are not doing anything with magnetic energy. The electron has, so we aren't turning on a magnetic field. In that case, the Hamiltonian, in other words, the operator for the energy of H2, does not have in it any spin-dependent terms. It doesn't have any energy which would indicate that spin up is different than spin down. If we turn on a magnetic field, then there are energy terms that depend on whether spin up or the electron is spin up or down. And in that case, we have to be careful because we have to include those terms in the calculation. But for us, we don't have to do that. And so the spatial part of the Hamiltonian, which is what we're going to focus on mostly, is just a product of the molecular orbitals 1sa1 plus 1sb1, or we could make it more elaborate. We can always expand each starting molecular orbital that we start out with times the same thing for the second electron. And I've called this whole thing then psi-MO, which will be the spatial part, 1 over 2 times 1 plus s, and then this product of these orbitals. If we do this, our molecular orbital picture predicts a bond that's not too far in error, although it's by no means perfect. The dissociation energy is not perfect, the bond length is not perfect, but we do predict a bond for H2, and so it seems like everything is okay. We can solve for the total energy as a function of R with these 2 electrons in. Just like we did for H2+, we treat R as a parameter, we move the nuclei, we fix them, we solve for the lowest energy, we put a point there, we move the nuclei again, we solve again, and so forth. And it's just the same thing as we did for H2+. However, if we do this, something pretty odd happens. As the atoms get farther and farther apart, the energy of H2 does not go to the energy of 2 isolated H atoms, because that would be minus 1.0, minus a half for this hydrogen, hydrogen A, minus a half for this hydrogen, hydrogen B. That's not what happens when we take this molecular orbital, which is our simplest one. And therefore, something's wrong, because for atoms, we really looked at predicting the correct ionization energy as part of the measure of quality as to whether we had the right idea or not. If we couldn't predict the ionization energy, then we'd think we were, something was wrong. And in fact, something is wrong, but what's wrong here is a little bit more subtle. So it seems like for some reason, because as I'll show you in a second, the energy is way off. that we've done something inadvertently wrong, because there's something about it that we still don't quite understand. So it seems like when we look closer, we've still got sort of a structural flaw in our approach. And this is a very important structural flaw to appreciate. If we take zeta equals 1, the minimum energy of H2 is minus 1.0991 Hartree at the minimum radius of 1.603 A naught. That's if we do everything properly, do all the integrals, optimize it, that's what we get. If we let zeta vary, of course it expands a bit like it always tends to, and we get zeta 1.193. The minimum energy now improves to minus 1.1282, and the radius improves too to 1.385 Bohr radii. The accepted values are minus 1.1744 for the energy and 1.401 for the internuclear separation, R sub E. The R sub E we predicted by optimizing zeta is smaller, but keep in mind the variational theorem refers only to the energy. It doesn't say that the internuclear distance always has to be greater than the correct one. It just says the energy is always higher than the correct one. And so there's nothing wrong with predicting a tighter arrangement of nuclei. That's nothing to worry about. However, if we take our same equations and we just let big R go to infinity, boom, out like that, then the energy goes to a limiting value of minus 0.7119. That's what we get. And that's way off minus 1. Something is wrong. We're predicting an elevated energy in the limit, and we have to take a look at that, because that's way too far in error to just brush off as something. And in fact, even if we make our orbitals much more elaborate but keep the same structure, we still get a very bad answer for the bond dissociation energy, if you like, for H2, taking H2 and producing 2H atoms. It must be then that we're doing something that is different than that. And to see what we're doing, here on slide 605, what I've done is I've expanded out all the terms. We have the product of the electron 1 and its MO, and then electron 2 in its MO. And here's what we get. We get 1SA1, 1SA2. And then we get 1SA1, 1SB2. And then we get 1SB1, 1SA2. And then we get 1SB2, 1SB1, 1SB2, excuse me. What do these four terms mean? Well, let's just look at them. The first term, 1SA1, 1SA2, what does that mean? Well, that means both electrons are on nucleus A. That's what that term means. And that means there's none on B. This first term, which is 25% of the total, is 2 electrons over here and none over here. And then what we've got in the middle is we've got 1 electron on A and 1 electron on B, and then we've got 1 electron on B and 1 electron on A, just the other way around, because we're labeling the electrons, but that's the same. And then the final term here, which is another bad one, is 2 electrons on B and none on A. Well, this is the form of our molecular orbital, and we can interpret these things when we square them up as the probability of the electron. And if we let the 2 atoms get very far apart, of course, when they're close together, everything's okay. All the wrinkles are smoothed out. But when we let them get very far apart, it's quite a different story, because now we've got a big problem, and the big problem is this. We're predicting 4 possibilities when we dissociate H2 using this particular wave function. We're predicting we either get H minus and H plus, or we get 2 H atoms, those are the 2 center terms, or we get H minus and H plus. And the dissociation of H2, what we want to think about is producing 2 H atoms, not producing these weird excited states, hydride being barely bound, and then a proton on the other side. And yet these come out in our wave function, in our molecular orbital. And therefore the problem is that the way we've set this up, which seemed to be a very good way, the most obvious way to do it, is no good because it includes too much ionic character. It says half the time you get H plus and H minus, and the other half of the time you get 2 hydrogen atoms. That's not, in fact, what we want to happen. But if we know that, then we can rationalize why the limit comes out wrong, and the way we can do that is, well, we sort of had the foresight, you might even think it's planned, to calculate the energy of the hydride anion earlier on. So we can go back to our notes on that, and we've got that down pretty well. So we can take that. The energy of a bare proton at infinity, at rest, has no electrostatic energy at all, because the potential energy is 0 and the kinetic energy is 0. It's just a bare proton. And so we can figure out what's going on. The optimum value of zeta is 1.0 for a hydrogen atom, because that's where it came from. But for the hydride anion, we found out with a variational approach that the optimum value of zeta was 11/16. So there are 2 of each form. A hydride, H2, 2H, 2H, and then a hydride. And so the average value of zeta should be 1/4 of 2 times 1 plus 2 times 11/16. If we work that out, then the zeta bar, if you like, the average value should be 27/32, which is about 0.84375. And that's in fact the optimum value of zeta as you go to infinity. That's the one that comes out of optimizing zeta as you keep changing big R. And also we can explain why the energy has that particular value minus 0.7, because the energy of a hydrogen atom in a Slater orbital is zeta squared over 2 minus zeta. And we found for hydride that the energy in a Slater orbital is zeta squared minus 11/8 zeta. That's how we optimized it, if you recall. And there are 2 H atoms produced when H2 separates, 1 H minus and 1 H minus, with the H plus having no electronic energy. So if I take 1 H2, you get 2 H atoms when it separates. But if it separates this way, you just get 1 hydride and nothing. Now you want to include equal parts of those. So there are 4 terms, but we only need 2. We don't need to do the other 2 because they're the same. So what I want to do to figure out the energy as this thing falls apart in this orbital is 1/2 times 2 times the energy of a hydrogen atom plus the energy of a hydride. And if I do that and I put in the zeta squared minus 2 zeta and 11/8 and everything, what I find is that the energy of the MO as R goes to infinity should be zeta squared minus 27/16 zeta. But we know what zeta goes to because we just figured that out. We said, well, it should go to the average, 27/32. And so we go ahead and put in 27/32 into the formula, And what we get at the end after simplifying it is minus 27 over 32 quantity squared, which is minus 0.7119. Exactly what is observed when you look at the numbers. So sometimes numbers hide a lot. So, they seem to be just a number from nowhere, and yet here it is. It's exactly 27 over 32 squared, and it's no coincidence that it has that value. Well, we can let R go to 0 too. If we let R go to 0, what we're doing is we're compressing our H2 into a helium atom. This is the great thing about doing thought experiments, is that you can do whatever you like and you can see whether it makes sense or not. Now, of course, what we better do is we better throw away the 1 over R repulsive term if we let big R go to 0. And that's because when they touch, we're assuming the strong force takes over. And there would have to be some neutrons, but they don't change our electronic energy at all, so we don't have to really worry about that. In that case, we have essentially a helium atom, and what we find is that our parameter zeta for the orbital goes to 27 over 16 as R goes to 0. And that agrees with the calculation for helium exactly. That's exactly what we found. So the problem with the dissociation is that we're including too much H plus and H minus in the products. And that's because of the way we set up the linear combination of atomic orbitals, molecular orbital. It's just too much. It shouldn't be that much. Now, as far back as 1927, Heitler and London were trying to explain chemical bond, and they wrote something which I'm going to call psi VB for valence bond, and they wrote just 1SA for electron 1 times 1SB for electron 2 plus 1SB for electron 1 times 1SA for electron 2. This seems very similar to the kind of trick we used when we finally got hydride to give an answer. And in fact, if you use this particular wave function, you can show that there is a chemical bond that exists and as a pair of electrons, and this led to the so-called valence bond theory, and we're going to talk a little bit about that coming up in a more qualitative way, because in a certain sense it seems like whatever happened to the bonds, whatever happened to the lines between the letters and the arrows moving electrons and all the things that you might have done in organic chemistry, it seems like that stuff has sort of disappeared like the Cheshire cat. But it's coming back, don't worry, because we can actually incorporate our much more formal and insightful view of bonding to go back to a much more simplified view when that's expeditious. Usually, computer programs are going to use molecular orbital approach. So the valence bond approach is mostly of historical interest, but is not really used in modern computational programs. But it is very important because it does suggest how to improve. Instead of having the 50% ionic H plus H minus that we had with our molecular orbital, what we could try is a new wave function, which is C1 times psi valence bond plus C2 times psi ionic. And then we could optimize C1 and C2 and get a better result. And we know how to do that by now with the variational principle. And we've done that many times in this course already. In fact, though, it turns out there's a slightly different way of looking at this. And it turns out that what we ought to do, it seems a bit counterintuitive, but what we ought to do is include a bit of the anti-bonding orbital. Remember, we had the combination plus plus and plus minus that had a node. If we include a little bit of the anti-bonding orbital in the mix, in a scheme called configuration interaction, or just CI, then we can get a much better result. That turns out to be rather similar to taking this valence bond and ionic approach, but let's just look at it in this way. If we include CI, then we can get the right dissociation limit for H2. So this solves our problem. Here's what we do. We write that psi, now I'll call it CI, for configuration interaction, is equal to some coefficient times the bonding orbital for electron 1 times the bonding orbital for electron 2. Good, that's that part. That's what we had before. But now what we're going to do is we're going to expand our basis set to include C2, some admixture of psi star anti-bonding for electron 1 times psi star, sigma, I'm using sigma, not psi, for electron 2. And these are just because it's called a sigma bond, and it's either bonding or anti-bonding. And I know what these sigma B and sigma A are. One of them is 1SA plus 1SB, and the other one is 1SA minus 1SB. And I can multiply all these things out. And what I get then is C1 times 4 terms, the same 4 terms I had before, SA1, SA2, SA1, SB2, and so forth. Plus, I get another term, C2, with the anti-bonding, and interestingly, I get 1SA1, 1SA2, and then the others have the opposite sign, and then 1SB1, 1SB2, and that's just because of the symmetry. So the terms are very similar. A few of them change sign, and if I include more in my starting orbital, and then I optimize the amounts of each, you might think, well, if you pick an anti-bonding orbital, it's going to come out 0, because after all, we called it anti-bonding. But that's a little bit naive, because as we'll see, that's not quite how it works, because C1 and C2 depend on R. And so they turn colors and change as we change apart. And it's this extra flexibility of having C1 and C2 vary that lets us get out of this soup. So I'll just cut to the chase. If I simplify this admixture then of the bonding and the anti-bonding, what I get is, compared to what I had before, I get C1 minus C2 times psi valence bond, what Heitler and London wrote, plus C1 plus C2 times psi ionic. So they're very closely related. I just get a linear combination of the two. But the difference here is that the coefficients themselves, C1 and C2, depend on R. When I change R now and I have my molecular orbital, I have to re-optimize every part of the molecular orbital. The mixtures that I allow, what percentages, the zetas, everything, because what in fact happens when the nuclei change position is the electron magically and quickly, a la the Born-Oppenheimer approximation, instantly finds the optimum orbital on its own. We have to find it by clowning around a lot numerically, but in actual fact in nature, it's instantaneous and it doesn't take any great calculation to do. What we find then, if we do this, is as R goes to 0, C2 goes to 0. That's perfect, because as R goes to 0, that means the anti-bonding part is out of our hair. As R goes to infinity, however, C1 goes to root 2 over 2, and C2 now goes to minus root 2 over 2. And what that means is that the second term, psi ionic, disappears. And by substituting in the coefficients, what we can see is that this configuration interaction wave function gives the correct answer for helium when R goes to 0. And it also gives 2 hydrogen atoms and nothing else as R goes to infinity. And that's perfect. That means that we've solved our problem. Now the energy after dissociation is correct, and we've got no more conundrum. Of course, we could start all over. We did this with 1SA plus 1SB. We saw before that even for H2 plus, we should include 2PZ. We can go back, we can put that in, we can then take bonding and anti-bonding and so forth. And boy, it gets complicated quickly, but we get excellent results. So if you're willing to work harder, you get better answers. It's kind of satisfying. For the simplest calculation then, wrapping up H2 with zeta equals 1 and not optimizing it, we get the energy, what I'll call ECI for configuration interaction wave function, is minus 1.11865, and the radius is 1.668 A naught. This is better than our first try with the bonding MO. If we optimize zeta, then it increases and the energy becomes smaller, minus 1.14794, and the radius, the internuclear distance, is now 1.43. And if I put in more atomic orbitals, I essentially get the correct answer to as many digits as the experimentalists can tell you what it is. But of course, you need a computer to do that, because you just have many integrals to do, and you can't hope to do them all by hand. And then you have, even after you get them done, you have a messy optimization problem, which you may need some fairly sophisticated methods to solve. But that all can be done, and you get a very beautiful answer. So here's our qualitative picture. If we start with 2 atomic orbitals, we end up with 2 molecular orbitals. And we can summarize things then with this qualitative picture here on slide 617, which is a molecular orbital diagram, which some of you may already have used without understanding exactly what it meant in detail before. We start out with the energy on the ordinate, and we put lines for the energy of the isolated atoms. We have 2 hydrogen atoms, so they have the same energy. But keep in mind, if you have 2 different atoms like C and O, then all the levels are shifted, because oxygen has a much bigger positive charge in the center, which is pulling down orbitals. So you mustn't assume if you call an orbital 2pz on oxygen that it has the same energy as 2pz on carbon. They do not. But here, out of symmetry, they do. And then we take a good combination, which is lower in energy than the 2 isolated atoms, and the bad combination, the anti-bonding, which is higher in energy than the 2 isolated atoms. And then we draw 2 electrons in. And to be strictly correct, it's probably better to draw half arrows for the electrons, so that a full arrow with a full point on the end means move 2 electrons, because when organic chemists write their reactions, they're usually having bonds move, sort of like a mousetrap snapping onto another atom, and they denote that with a double-headed arrow. So, but that's kind of difficult because PowerPoint, for example, doesn't have a half-headed arrow. So you have to make them by hand. I took the trouble to make a few by hand here that I've put in. The lines in between, like the tennis tournament, all they are meant to qualitatively indicate is which orbitals are present in the linear combination that's giving either the bonding or anti-bonding orbital. And nothing more than that, really. I mean, to actually know the amounts, we have to do some kind of calculation. We can't just guess what amounts go where very easily. The energies themselves, unless they've been calculated somehow and drawn for you, if you're just drawing them yourself, the energies are guesses. And you have to keep in mind that they move around a lot as you add electrons in. So you mustn't just assume that a molecular orbital is like a static tennis tournament or something and then players defeat each other. It's not like that at all. They move around. The actual tournament itself moves around, and sometimes things that were above in one combination go below in another. We'll see that in the next lecture. The bond order is an important concept when you look at a molecular orbital diagram. It's the number of bonding electrons minus the number of anti-bonding electrons divided by 2. And for H2, we've got 2 bonding electrons and 0 anti-bonding electrons. So the bond order is the average, or divided by 2, of 2 minus 0, which is 1. Therefore, we would predict a single bond for between 2 hydrogen atoms, and that's why we draw one line. Usually if we're talking about double or triple bonds, we draw 2 or 3 lines. For H2 plus, where we only have 1 bonding electron, the bond order is 1/2. That explains why it's very weakly bound compared to H2. And for helium-2 dimer ion, He2 plus, where there's 3 electrons, there's now 2 in the bonding and 1 in the anti-bonding, and so the bond order is again 1/2. For He2, there's 2 bonding electrons, and there are 2 anti-bonding electrons, and therefore the bond order is 1/2 of 2 minus 2, or 0. If the bond order is 0, then what we're predicting is no bond. Basically, 2 helium atoms trying to form a bond have about the same energy as 2 helium atoms without the bond, and so why should they do it? They'd prefer to maintain their independence from entropy considerations. These are really qualitative pictures, because as we add more electrons, we have all those 1 over R12, 1 over R13, 1 over R23, and we never did any of those integrals. We just kind of kept the same qualitative picture here with these 2 levels and started pumping in electrons. But in actual fact, they'd move around, and if we want to get it right, we'd have to actually do some work and figure it out. But if we make quantitative measurements, so here are some accepted data. For H2 plus, our configuration is 1s sigma G1. The bond order is 1/2. And in fact, what's measured is the bond length is 106 picometers, and the binding energy in chemist units now of kilojoules per mole is 269. For H2, we have 1s sigma G squared, and the bond order is 1. The bond length is 75 picometers, and the binding energy is 458 kilojoules per mole. For helium-2 plus dimer, we now have a 1s sigma U, that's the anti-bonding, as well as the other one being full. The bond length is back to 106 picometers. That's probably a coincidence. I don't see why it should be exactly the same. And the binding energy is back to a similar value. For He2, where we have both of them, the bond order is 0. The bond length is listed as 6,000 picometers, and the binding energy is listed as about 0.01 kilojoules per mole. Well, what that means is that physical chemists are very stubborn, and if you say you can't make a bond or you can't make something stable at all, they will try very hard. And so it could be that there is an experiment where you cool down 2 helium atoms and you make sure nothing else is around, and there's just those 2, and they have minor fluctuations of charge, and so they kind of vaguely attract each other at this very, very long distance, and people like to do that the same way they like to get a gigantic telescope and see how far they can see out into the universe. But that doesn't mean that the helium dimer it exists under normal circumstances. It does exist in this very esoteric way with these very specialized experiments that have been done by experts, but we'd never see the helium dimer under ordinary circumstances, and that's why we consider helium to be a fairly ideal monatomic gas. Okay, we'll leave it there. We're done now with our sort of very detailed exposition of bonding in these simple systems. And of course, to make it detailed, we had to have a simple system, because if we have 3 electrons on this atom and 8 on that, we can forget it. We're going to have so many integrals to do, and it's going to take forever. And so what we have to do is learn how to zoom in on what's important and leave the rest of it aside, especially if it's going to be a ton of work. We don't want to end up digging a ditch with a teaspoon. That's a very bad idea. We just want to cut to the chase and say, look, here's the core, here are the valence electrons, here's what we have to calculate, here's how accurately we have to get it, and here's qualitatively what it means in terms of structure, bonding, and reactivity. So we'll pick it up next time. We'll actually get to the second row on the periodic table, which will be exciting because there will be some chemistry aside from hydrogen and helium, which is a little bit boring to stick with this long.